lab meeting. So in this lab, we will cover some activities on the meeting of yesterday, wireless communications. Start by the first activity, the sampling rate. So we have already studied yesterday that when we need to convert or to transmit some analog signals, so we need to carry some sampling, okay? And after that, the quantization. So here you are asked, you have a signal extends from very low frequencies. Okay, so the frequency of your signal now is 8 kilohertz. So what is the minimum sampling rate required? Okay. So as you know, there are some rule that tells the Nyquist, okay, formula. It tells that when you have 8 kilohertz, so you have 8,000 of hertz, so you need to sample at more than the double, okay, 16,000 times per second. This is the minimum, okay. It is called the number of Nyquist. The number of Nyquist is the minimum number of sampling rate required to recover your signal at the receiver, okay. So this is your signal, for example, okay. This is your signal. This is the time here, T, and this is the amplitude, okay. Imagine that this is your signal. So what is the period here? What is the period? This is the period, okay. Okay, so this one is called the period. The period is the number of cycle, okay, in one in times, okay, in seconds, the number. So okay, so imagine that you have here 8 kilohertz. So what is the period here? If you have the frequency f, the frequency is equal to the inverse of the period, okay. It is 1 divided by t, the period t, okay. This is t, the period. So the frequency is the inverse of the period. So here you will have 1 divided by 8,000, okay. It will be how much in seconds? Is equal to 1 divided by 800,000, sorry. It will be equal to 1.25 millisecond. 1.25 millisecond, okay, millisecond. So we can here have some the time in millisecond, okay, and this is the period is equal to 1.25. So at least you need to take one sample from this side and one sample from that one, okay. We cannot take lower than that, okay. So this is the minimum number, okay. And as the number of sampling becomes bigger, okay, so the fluctuations, okay, the samples will represent all the fluctuations of the signal, okay. So is it clear? Okay, move now to the activity number 2. After sampling, we will carry some quantization. So we will use bits, okay, to code, okay, code the different, okay, samples. So here you are asked how many bits per code word are needed to code the levels in the two parts of the following. So you have this part and this one, okay? Part 1 and part 2. This is part 1 and this is part 2, okay? So in the part 1, how many levels we have? Look, how many levels? This is the levels, okay? This is the different levels that you need to quantize, to make quantization of your samples. So we have 1, 2, 3, 4, 5, 6, 7, 8, and 9. We have 9 level. Okay, so how many bits you need, okay, to code this level? How you can get 9 in the in number of 2 power number, okay? So as you know, 2 power 3 is equal to 8. So if we use 3 codes, 3 bits, so we can represent 8 levels. Now we have 9 levels, so we need 2 power 4. We know we need 4 bits. Okay, 2 power 4 is equal to 16. Okay, so we will use 9 levels. Okay, 9 numbers. Okay, or code word. Okay, and the others will be discarded. Okay, is it clear? This is how we can calculate the number of bits. Is it clear? You need the repetition of what? Yes, Adi, I don't see your question. Is it here or the activity 1? Activity 2, okay. So here we have how many levels? We have 9 levels, okay? This horizontal lines, okay? We have 9 levels. So we need now to choose the correct number of bits to code this level, okay? You have 9 levels, so you need to represent this 9 level with codes. When you use 2 bits, imagine that you have 2 bits, okay? So how many combination you can have? 0, 1, 0, 0, 1, 0, and 1, 1. So you will get 2 power 2, 4 levels, okay? When you wish to represent 9 levels, so you need to have, okay, to choose the right number of bits, okay, that you can have 9 combination of 0 of 1. If we use 3, 2 power 3, 8. So you will have 8 levels, okay? But 9 is greater than 8. So we will use 4 digits, okay? 4 bits, and we have up to 16 levels to represent, okay? But here we need only 9. So 9 levels will be used and the others will be not used, okay? Unused. Okay, so we have 9 level are needed, okay? This would require 4-bit words and this gives 16 levels, so some would be unused. On the right here, on the part 2, you will have 33 levels. Okay, so you need a 6-bit because 2 power 5 is equal to 32. Is equal to 32, okay? So you have 1 level missing, okay? You cannot represent one level, so you need 6-bit. Again, some of the words would be unused, okay? So we will use only 33, and the remainder, okay, will not be used, okay? Okay, move now to the activity 3. In the activity 3, what is your question? You cannot choose less than the number of lines. But this number, in this number, you will divide your space with the correct form. Okay, so you need these levels. Well, so we go to activity 3. A speech signal of voice telephony is sampled every 125 microsecond. Okay, here you have microsecond. So you remember that 1 microsecond is 1 millionth or 10 power minus 6, okay, of a second. So if you have 256 quantization levels are needed per sample, what is the transmitted bit rate? Okay, it means how many samples per second will be taken and how many bits are needed to represent each sample. Okay, so because we have 256 quantization levels, so how many bits you need? 256 is equal to 2 power how much? So this is the number of bits that you need. Okay, this is 6. So 2 power 5 is equal to 32. 2 power 6 is equal to 64. 2 power 7 is equal to 128. And 2 power 8 is equal to 256. Okay, so you need 8 words. Okay, 8 levels. Okay, so if the signal now is sampled every 125 microsecond, so the sampling rate will be equal 1 divided by this number of samples is equal to 8,000 sample per second. So we will take 8,000 sample per second. Okay, so now when you have 256 quantization levels, so you will require 8 bit words. Okay, so the bit rate is equal to 64,000 bits per second. Okay, because you have 8,000 samples and each sample will be represented by 8 bit. So you will have 8 multiplied by 8,000. You will have 64,000 bit per second. It will be equal 64 kilobit per second. Okay? It's okay? Yeah, good, good. So you need here to calculate the numbers of samples, and each sample will represent by 8 bits. Okay, so this is the number of bits, okay, per second. Okay, move now to the activity 4. So if the throughput of a Zigbee device is 210 kilobits per second, so how long would it take to transfer 2 megabit of data? Okay, remember that 1 kilobit of data, kilobyte, sorry, is equal to 1024 bits, and 1 megabyte is equal to 2 power 6, okay? Sorry, 2 power, this power 10, okay? This is 2 power 20. Okay, this is not like the lowercase kilo. The kilo here is 10, is 1000. And the mega here, okay, here megabyte is equal to 1 million. Okay, it is used to measure the bits per second. Okay, but here the mega is not capital, huh? It's small, the megabit. Okay, when we use the capital representation, it means that we use the binary system. Okay. Okay, first we will express, okay, these numbers in the same units. Okay, so 2 megabit of data, megabyte, is equal to this number 2 multiplied by 2 power 20, okay, is equal to this number of bits. Okay, now we have this read. Okay, so this read, we have already the data rate. It is the size divided by the time. The size divided by the time. Okay, the read. So once you have the read and the size, you can exchange. So the time is equal to the size. This is the size of the to the size of the file divided by the rate, which is equal to 210 kilobits per second. Okay, 210 here. Okay, the rate. Okay, so it will be equal to 80 seconds. You need 80 seconds to transfer this data, this amount of data. Okay, is it clear? Is it clear? Do you have any question? Any question? Okay, move now to the activity 5. So the maximum data rate of a ZigBee is specified at 250 kilobits per second, and the Bluetooth maximum data rate is 1 megabit per second. Okay, so how many times greater is the Bluetooth maximum data rate than the ZigBee maximum data rate? Okay, so you need to have how many times? Okay, so look, we first to express both figures in the same measure, okay, in the same units. So here we have kilobits per second, so here we have megabits per second. So 1 megabits per second is equal to 1 million bit per second, and 250 kilobits per second is equal to 250 thousands of bit per second. Now we will divide the Bluetooth, okay, by the ZigBee data rates, okay, and we will get this number 4. So this means that the Bluetooth maximum data rate is 4 times greater than the ZigBee maximum data rate. Okay. Okay, is it clear? Clear or not? Okay, move now to the activity. To change the kilobits for 2 kilobits. Yes, you can. Yes, you can. But you need to divide here the kilobits to go from kilobits to megabits. Okay, you need to divide by 1000. Okay, so here you have 1, and here you have 0.25 megabits per second. So it is the same. You will have 1 divided by 0.25. Yeah, we can. Move now to the parity check. So which of the following may be valid code towards using even parity? So look at the A. Is it valid or invalid? Good, Muhammad. It is invalid. Why it is invalid? Because it is invalid. Yeah, because it has an odd number of ones. Yes, good. Odd number of ones. Okay, so this is invalid. Okay, for the B, 01001101. It is valid or invalid for the B? Yes, good, valid, valid. Why it is valid? Why it is valid? How many ones we have here? Okay, even number of ones, it is 4. 4 is an even number, so it is valid. Not binary number, even number. Okay, for the C now. It is valid or invalid. So here it is valid, okay? For the C, it is valid or invalid. C. Yeah, invalid. Why? Because we have an odd number of ones. We have 5 ones, okay? And 5 is an odd number. For the D, now, D. For the D is D valid or invalid? Yes, invalid. For D is invalid because we have 7 ones, okay? And 7 is an odd number, so it is invalid. We need an even number, okay? For the E is valid. Good. We have 6 ones, so it is an even number, so it is good, okay? Okay. Do you have any question here? Move now to the last activity. Fill the right parity bit. Now, the right parity bit. If you have these 7 bits, so what is the right parity bit if it is 0 or 1? Okay. So how we can fill the parity bit? We need to, if the number of ones is even, so we need to put 0 in the parity bit. If the number of ones is odd, so we need to add 1, okay, to make the number even. Is it clear? For A, we will add 0 or 1 for A. Sadia tells that we need to add 0. Are you agree with her? Yeah, here 0. Why we use 0 here? Here we need to add 0. Why? Because here we have 1, 2, 3, 4. We have even number of ones, so we need to make it even, okay? Here for B now, for B, what is the parity bit? The right parity bit for B. So in the first, you need to add the number of ones. It is 1, 2, 3. 3 is an odd number, so we need to add here 1 to make the number of ones even, okay? Is it clear? Okay, good. For the C now. For the C. For the C, we will add 1. Why? We will add 1 because we have 1, 2, 3, 4, 5. 5, 1, okay? So we need to make the number even. We will add the 6th one, okay? Good. For the D. For the D, we will add 0 or 1. For the D. Okay, good. We need to add 0 because we have 6 1. Okay, so we need here to add 0 as a parity bit. And for the E, okay, so it is the same as D is 0. Okay. So do you have any question? This is the end of this meeting. These activities. Do you have any question about labs? If you need some clarification, some... okay, I will do. Other questions, queries? What? What? No, in the final you have all the course with you for the final. The final? Yes, I think there are some activity to solve. I don't know what is the type of questions, but I think it is rather right algorithm, perhaps some blocks, okay? Which one? Here for the link 1, you have 2 links in the TMA. So link 1 for the Word file and the second link for the zip file, in which you will regroup all you build scripts in one folder, compress this folder, and okay. Any questions? Thank you very much.